Okay, so apparently this session is not going to be overcrowded. So I guess we can slowly start. Let me close the door. It's the last session of the conference, so maybe some people already went home, and definitely it's not a very popular topic. But the important thing is that some people have good usage of it. So in previous talk, you saw that I was focusing on constraints. I was focusing on enforcing data integrity. However, during this effort, I actually introduced some potential performance problems. So basically, the biggest performance problem was with queries. Suddenly I have these predicates that are not searchable. So even if I have an index, it doesn't help me. I get full table scan. And also to mention the size of the unpacked forum, please. The size of the unpacked forum could be problematic. So in this part, okay, I will not present myself anymore. In this part, I will discuss different options for optimizing this kind of queries. So getting to indexing, getting to efficient reading, and also discuss how you can create kind of compact unpacked forum. So a brief introduction. Most of you have visited the previous session, so you know we have temporal tables, many things like contracts, appointments, and so on. And here we have intervals. And of course, we also mentioned that we can have also intervals that are not only intervals of time. Okay? So common problem, this is what we also discussed in the previous session, is when the two intervals intersect or overlap. And we said that overlapping operator is the most complex of all operators that we defined. So if we solve problem with overlapping, we are automatically solving all other possible queries. So we'll focus on this problem, how to optimize queries when we are searching rows. So you know we have a big table with a lot of intervals from to begin end, and we have a given interval. So we are searching all rows where this given interval overlaps with my intervals in table. And in previous session we introduced interval SID data type, which has overlaps operator and makes this kind of queries very simple, unfortunately also inefficient. So unfortunately simple in this case doesn't mean also performing well, because this is a CLR data type operator, SQL server, your column that is indexed is inside the function, inside the CLR method. So this is not a searchable argument, although you would have an index. And I will also show you that this kind of queries will produce full table scan. And of course, these are common problems, searching for contracts that were active during an input period. So you are searching all contracts for which their interval overlaps with your given interval. So let's start with classical representation. Classical representation when we have two columns, not the interval data type. I will discuss also possible implementations, possible optimizations of this kind of solutions. You are not limited to interval data type. So we have lower and upper boundary of the interval, ID, and of course multiple other columns. And now we can even produce best possible indices. So we have index on key, where key is the lower boundary and includes upper. So this would be covering index if I have, let's say, clustered index, primary key clustered over ID. This would be covering index because it also includes ID. And also if I search from the other direction, I can create the different index key of that is the upper boundary or end of the interval and includes the beginning or lower boundary. And let me start with this classical solution immediately. So I will show you the first demo. And since I'm working now with huge amount of data, I actually created a lot of things in advance, so I will show only queries. So I created a database, okay, and then some auxiliary function to generate numbers, and then staging table which is filled with random intervals, okay, with random intervals from begin and end time points with integers. We discussed this theory behind in the previous model and realized that we can use integers because there is functional translation from integers to time points, okay, or from time points to integers. And also, this table has a lot of rows, 10 million rows. Okay. Now this is kind of staging table that is used to populate many different other tables. So all tables have the same data. So the comparison is completely fair. So first solution is this intervals table, ID lower upper, constraint that upper must be greater or equal to lower, and then just inserting from stage table primary key cluster at over ID and these two indexes. Key, where key is the lower boundary and includes upper, and the opposite where the key is the upper boundary and includes lower. And you see already this took some time, so that's why I populated this in advance. So here I have this 10 million rows, and I have 10 million rows, minimal, maximum value, right? And please note that this is the maximum length of an interval in this case, it's just 20. I will explain later what to do if you have bigger intervals. But for now, this is limited because I want to get as much performance problems as possible. Okay? So let me set statistics on time on, and let me query this data. So I will start from the beginning, and I have also execution plan. So you see my intervals start at 3 and finish, I don't know, with big numbers. So this must be somewhere in the beginning of the table, of the index that starts with the lower column, okay? So I'm searching all of the intervals that overlap with this interval. So if I would quickly draw how it looks. So I have all of this kind of intervals in my table, right? This is lower index. So my search index is actually used to check only this part. So I can easily cut off from further analysis vast majority of rows. What does it mean? Let's execute this query. And option recompile is used to be sure I don't want the plan to be reused because I want a different index to be used when I'm searching data from the other side of these intervals. So let's start with the beginning of the data. So I returned 30 rows, see here. And what was the disk I/O? Well, 3 logical reads, that sounds pretty good. And let's see execution plan. So in this case, of course, the index on the lower column was used because this index could successfully cut off the vast majority of rows from on the right side. You see? So I got very efficient query. No problems here. Let's go to the end of the data. So we are searching intervals from the right side, and that's why I have option recompile. So I'm sure that I will get the best possible execution plan. Now I have 27 rows, okay, from the right side. And let's see, again I have only 3 logical reads. However, this time, you can already see here, upper index was used. Okay? And upper index managed to successfully cut off vast majority of rows from the beginning. Okay. Yes?
And you try and use both the side versus best, don't it?
Well, you see, this is our problem. This is the biggest part of this problem, because SQL Server accesses one table in a query in one way only. So you see, it decides either upper or lower index, or full scan. In this case, I cannot get full scan because I have covering indexes, so I can get non-class covering index scan only. Okay. Now let's go to the middle of the table. And here is the problematic part. You see, now if no matter which index I take, now I'm searching something from here in the middle. So if I take upper index, I can successfully cut off these rows, but still have half table to scan. If I use lower index, I can successfully cut off these rows, but have to do half of table scan from this side. And you see, it doesn't even make sense to use both of indexes. So what would you do? First, read half of the rows from the lower, then half of the rows from the upper, and then join. It's simpler than to do full scan anyway. See, this is the problem. Whatever you do, you have to do at least half of the scan. And this is exactly what happens. I have option recompile, so I'm not really sure which index will be used, but anyway, whichever one will be used, I get this. So full table is approximately 22,000 pages. Okay? So let's just check this one. Oh, let's first see execution plan. Okay, it was parallelized, not a problem, because I'm the only user here. So apparently here was the lower index, object was upper. Apparently upper was slightly more efficient, but still it managed to cut away only half of the rows. Yes, please?
You decided 50, was it 5 million and 20 as your boundaries. If you slid that slightly back and said 49999.
Yeah, then maybe lower would be used. Yeah, so maybe let's slide, let's say, a little bit more back, so to be sure. In this case, I guess lower should already be used. And the more I go to the beginning, or the more I go to the end, the more efficient the query should be. So you see, it already has less logical reads. And yes, you can already see the lower was used. Because now I could cut off more rows from the right. But anyway, this is the problem. In this worst case, somewhere around middle, I have to scan half of the table. And this might be a problem. No matter which index I take, this is approximately half of the table. So we need some kind of solution for this. Now, I already mentioned this development in the previous session. Aaron defined interval data type and what kind of operators it should support and what kind of algebra in 83. Around 2000, and the book was out 2001 or 2002, Darwin and Lorenzos developed the full theory how to implement temporal data, including all of the constraints. And then also in 2000, the first try of optimization was introduced by Krieger, Petka, and Seidel from Munich University. So they invented the relational interval trees, and I will show you what was the problem of their solution initially. Building these trees was simply too expensive. Then just 2 years ago, 1.5 years ago, Laurent Martin found a way how to build this kind of relational interval trees in linear time. So last year, okay, then physical implementations, 2008 I wrote all of the theoretical implementation without any optimization. Was not known any optimization at that time. And then Itzik took this work from Krieger, Petke, and Seidel and Martin and created relational interval trees inside SQL Server. This is slightly going away from the original problem, up using spatial data in the library. And then last year I found more solutions for optimizing this. And this year I'm working on another solution. So this was the problem. We have two range predicates. You see, this was the definition of the overlapping interval. So, start of one must be before end of the other one. If it's after, then they cannot overlap. But this is not sufficient. This is necessary, but not sufficient condition. Also, also start of the other must be before end of first one. Remember, if I go back to this picture, I already have all of this pens here. So, seriously, I got at home a lot of these pens from London already. They are to kind of travel with me, don't forget. So we have this situation, you see. So, this interval and this interval cannot overlap because end here is before this begin. However, it can overlap with this one because this begin is before the end. Just having begin before the end is not enough. This begin is definitely before this end. So this is not sufficient. So also the opposite must be true. So this begin must also be before that end, and then we can overlap. So we have two range predicates, you see, and I have index on lower and I have index on upper, but I can use only one access path. It wouldn't even make sense, as I said, to read half of the data from this index, half of this, and then join. Why, if you can then scan everything? So it makes no sense. So, also this option recompile was used. Otherwise, I don't want to get this parameter sniffing problem. I don't want to get plan reusage. No. Then also the queries, for example, I started with queries from the beginning where lower index was efficient. But then queries from the end would also use the lower index, which would be maximally inefficient, which simply means full table scan, not just half. But this is the best what you can do with this classical solution. This is kind of the best. Now, what is relational interval tree about? It's kind of virtual binary tree. Virtual. Now, this is stored as a single column in a database, I will show you. But this is the virtual binary tree. So I have interval, for example, from 9 to 10. So for every single interval, I try to find something which Krieger, Petke, and Seidel called fork node. The number, minimal number, that kind of covers in binary tree the whole interval. So going up, this is covered by this minimal number 10. This has a fork node for this interval. Interval, for example, from 9 to 13 cannot be covered just here. So we must build one node up. So we must build additional node 12, which then covers all this. So also interval from 9 to 13 is covered. Interval from 9 to 17 cannot be covered with 12, cannot be also covered with 8. 8 can cover until 15. You see, this is binary tree simply. So I must build another level, 16. And you see, every interval has a fork node, a number, you see, that definitely covers the full interval in binary mathematics. So everyone has it. Here we have these two have this interval as this one. For example, interval from 3 to 11, you must go up to 8 that the whole interval is covered. Now this is the idea. If I have these fork nodes, so this is, you understand that this is kind of virtual tree because fork node is just additional column, one value. Okay? The lowest value when you build a binary tree with only binary calculation, okay? Say 1 time 2 on 0 degree plus, I don't know, 0 times 2 on first degree and so on. So this is this representation of the number, you see, in binary format. And this is just the number stored with the interval. So in a database, I have ID, lower, upper, and if lower is 5 and upper is 6 or 7, then number 6 is stored. Okay? If lower is, for example, 3, and or 4 also, because this could also be, 4 also covers itself, right? If the lower is 3 and the upper is 9, then 8 is stored. Okay? Together with this column. So this is the minimal fork node that with binary mathematics covers the whole interval. Now you can immediately understand the idea. Now I can index the fork node. And then I calculate the fork node for a given interval, the one I'm checking for overlapping. So let's say that I get fork node 20, okay? Or let's say to go even a little bit upper. I get fork node 24. So my interval I'm checking for overlapping is something like 20, because 20 is also covered with 24, 20 to 26 or 20 to 27. So the fork node for this given interval is 24. What does it mean? It simply means I can exclude immediately all of these fork nodes from testing. So I can include all intervals for which fork node is not covered by this fork node. Okay? So I can immediately exclude all of this left side. If I'm checking for a smaller interval that is covered by this fork node, means I can also exclude everything here. Now please note that if I have interval like 11 to 13, which is covered, this is what I'm checking, is covered with node 12. 12 is also covering everything from 9 to 15. So it means that after I did this pre-selection, excluded all of the rows here and all of the rows here, I must do exact matching on the rest of the rows. It's not enough just to get the correct fork node, because this fork node covers also intervals that do not overlap with given interval. So, for example, interval from 9 to 10 wouldn't overlap with interval 11 to 13, although they have both the same fork node. The same fork node covers both, right? So after I get the correct fork node for a given interval, I can seek for it, exclude everything, and then I still have to do kind of scan on the rest. But it's not so simple, it gets a little bit more complex. Now, first, this is the problem. You see, Kriegel, Petka and Zeidler said, okay, let's calculate this fork node, and once we have it, we can create an index, and then we can make these queries a little bit more efficient. Yes, but how do we calculate this fork node? So we start at the top, let's say with the highest possible integer, or some, if this covers 30 levels, and then go down, with classical bubble search, splitting in half, and check, okay, it's still covered, going next split, it's still covered, next split, it's still covered. Wow, now it's not covered anymore, I found a minimal fork node. So you repeat this calculation 30 levels maximally for every single row. Okay? And Transact SQL is not the fastest language for loops. It's not intended for this kind of calculations. Okay, you can say we could speed up this with a CLL function, and it's true, yes. C# is faster in loops than Transact SQL because it is intended for this work. But still, you need to loop this, well, let's say up to 30 times. And what if you have even larger intervals, then you have to even raise this. So simply building this kind of indexes might be too slow. Okay? Now, this is the work that Laurent Martin made. So he was playing with these bits, and I don't think even it makes sense to go to all of the details. Let me just try to briefly explain the idea. So you see, this fork node, you see, whatever it covers, the leading bytes are the same, bits are the same, 0, 1. Everything that covers has the same leading bits. And this one has leading bits 1, 1. So you see, this covers everything from 0, 0 to this is the highest possible leading bit. Okay? And from 1, 0 to the highest 1, 1, this covers all of these values. So this was the idea. So I take leading bits, and how many leading bits? Well, very simple, depending on the level you are. Cut off left rest of the bits, so I get these leading bits before trailing zeros. Okay? And then, you see, I simply know that all nodes before this fork node has the last bit 0 from this leading group, and all nodes after have the last bit 1. Okay? And so on. So this was the idea. And then, you can find from any interval, you can simply start by taking the higher value, cutting off all of the bits, adding zeros, and you get the node that covers the full interval. And this is very nice and simple mathematics. It might not be so simple. What is this? Doesn't work anymore. Okay. Not mouse problem, apparently it was a PowerPoint problem. PowerPoint was somehow stuck. So this is calculation, and as I said, this calculation is then, this is what is translated to Transact SQL. So this is the expression that actually calculates the fork node for every single interval using this idea. So now suddenly everything is doable. So this fork is then just computed column, which is calculated immediately when you insert or update a row. And you got this fork node. So just computed column and you get the actual fork node. So inserts and updates are fast, no problem. However, yes, the solution might be complex, especially if you want to use dates, but we already know that we can use integers. So this is nice. Now querying. Well, for querying, first we must find the actual node of the given interval. Okay? And then we go down the tree, and this must be done within in a loop, in an iterative approach. We go down by, again, splitting kind of bubble sort, until we find the minimal node that is covered, or that is covered by my search node. So intervals in this node, you see, minimal node from the left, intervals covered by this node can potentially overlap with my interval. However, remember that they don't need to overlap. So after I come there, after I find this node, I will still have to test every interval covered by this node, whether it really overlaps with my given interval. So for example, I have this node 10 that is covering, let's say that my search interval is something between 10 and whatever, something on the right. So node 10 is also covering interval 9 to 9, which is not overlapping. Now, this simply means that after I find all of the nodes that potentially can overlap from the left side, I put all of these nodes in a temporary table or table function. Then I join this to my original table, and then I still have to perform the filter, right? So upper part of the interval must be greater than equal than lower of my given interval, otherwise they cannot overlap. So I exclude like these intervals 9, 9, and so on. And now the same thing must be performed on the right side. So I must also search on the right side, down to the end, all nodes that are covered by my search node. And for some row, this is the one of these leaf nodes, for some row, this. And then I must exclude all those from the right side that actually don't overlap. So after I create all possible overlapping nodes table and join it, I still have to filter out. So altogether, I still have the original predicate. But then imagine that my search interval is very long. So let's say my right nodes would be here, my left nodes here. Then I definitely have some middle nodes that are fully covered by my search node. And these middle nodes definitely overlap with my interval without any need for additional check. These definitely just overlap. When I find node, they definitely just overlap with my interval. So actually my correct result is finding all of these middle nodes, and then left nodes, those who partially overlap, and right nodes who partially overlap, and union all of the data. All of the data. So what does it mean? So this was initial solution, which is not used, but this was actually used, the efficient calculated column persistent. So now we can simply create index on node, and even to have efficient search for left and right candidates also include lower and upper in the key. Okay, and you see that it was just slightly worse performing because of this additional calculation than initial table. So inserts, updates are not problematic. So this is what I got. So you see, node 4 covers interval 3 to 7. Node 12 covers interval 12 to 13. So for every interval I get node that covers it, and of course I still have these 10 million rows. And then I need to define left nodes, so I must find minimal nodes still covered, right? And find all of these nodes on the left side. right nodes, find all of the nodes from the right side. And okay, all of the nodes from the, this is an example testing from the right side. So these are the nodes from the right side that are candidates, right? And these are the actual, these are the right nodes that are candidates, and these are the actual intervals, okay, where I also added filter on the actual overlapping. Now, how does it look an intersection query? So, I have given interval, so I must find left nodes with a function, union with right nodes, and union with middle nodes, which don't need any specific function. So let's see the results. So in this case, execution plan is pretty complex, okay, because I have 3 queries. But you see, we are using left nodes function. This is scan, and then we have index used for seek in this interval relational tree for all of the nodes that are candidates for matching with the left nodes function. And similar for the right nodes. So what is the result? Okay, this is different because this is kind of randomized, but approximately the same. I have 133 logical reads in my table, and additional 2 logical reads needed to create left and right nodes. No, these are additional 2 logical reads used to scan left and right nodes temporary tables. This even doesn't show the cost needed to build these 2 functions. But remember, you are building them only once per query. So besides these 137 logical reads, there are some additional needed which are actually even not shown here to build this right and left node temporary table. But they are not so important. Anyway, what we can see that even this kind of query was suddenly much more efficient. And also, similarly, queries on the different sides would be the same, would have the same efficiency. So let's try something between, let's say, 10 and 30. And what is the efficiency? Similar 2 reads from both functions and similar efficiency in the actual table. I don't even need execution plan anymore, but I need the statistics I hope for further explanation. What is the problem with this solution? Well, I would say first of all, the problem is that this solution is pretty complex. Okay? So it's very, very complex. Let me go. Okay. First of all, it is very complex. Okay, you don't even need to understand how it really works once you have this node calculation, but every query is pretty complex. Also, I wouldn't say this is maximal efficiency. Remember, what can be our goal? What do you think? What can we achieve? Remember, initial queries from the beginning and end, they had only 3 logical reads. Can we achieve something similar in the middle of the data? So like 130 and more reads, and not even counting time and reads needed for building this is not the best possible. Of course, this is kind of logical. You see, I must say that I never really liked this solution. I read it years ago, but was never tempted even to try to develop the actual code. Because first of all, binary tree is inefficient by itself. Binary tree is the least efficient tree for search. So I said immediately, why? Why must be something better? Also, the solution is unnecessarily complex because it returns false positives. And while nodes, you still must do additional filtering. So every single query becomes complex like this, union of 3 queries. So yes, it is a solution, but I would say that it's not really the best possible solution. So, one good thing is that queries they always have the same efficiency, no matter where you search from beginning, from end, no matter where on the distribution of lengths of intervals. Okay? If the thing that matters is, of course, the length of the search interval, of course, but if you have very long interval, it will overlap with nearly every interval in the table, so you get table scan. Yes, this is what is expected. This is what you are searching for. Like 60% of rows, yes, this would be scanned anyway, so this is not a problem. But the good thing is that queries are always nearly equally efficient, so it's very predictable behavior. The bad thing is very complex query. Also, left-right nodes are not very efficient. Okay, and as I said, like the worst thing here, the thing I don't like, is that fact that every query becomes extremely complex. Now, next solution is the simplest possible you can get. And actually, you see, how I started to think, I said to myself immediately, I don't like this relational interval 3. But once it's implemented it, I felt challenged. Let's see, I always had a feeling that I can do better. So now it was time to do it. Now it was time. So Itzik published his article in April last year, and I was working on some project in April, but I was free in July, so started to work on this. This solution, first one, I was actually really surprised. I was Googling, Bingling over and over again because it is so simple that I couldn't believe that nobody thought about it before. And I couldn't find anything. I swear I didn't copy it from anyone. I was, kind of afraid even presenting this because I said, it's so simple. So how come that nobody came to this idea earlier? So what? I need to use a single index. Okay? That's what I need to use. So how can I use a single index? This is, let's say, these are my intervals, and this blue one is the searched one, the given one. So I'm checking which overlap with the blue one. Now, let's say that I want to use index on the lower side, right? So, index on the lower side, remember, efficiently cuts off rows from the right side, from the upper side. Okay? Because I can immediately search for those where begin is greater than the end of the given interval. Yes, these are, okay, immediately cut off. Now, on the left side, the condition is checking the end of these intervals. So my begin index is not efficient. How can I transform this query or this predicate in this way that begin would be efficient? Well, you see, I just must exclude all those who are definitely not candidates. And which are not candidates? Well, simply, I must exclude all those for which begin is lower than my begin minus length of the longest interval. So, this is the longest interval. So if I go here to the left, any interval that begins before this point cannot overlap with my interval, because it will end before my interval starts. So I can immediately cut off all of this And remember, I efficiently cut off this naturally. Of course, I still get false positives, so I still have to include original predicate. But now this is a single where clause. And let me show you this. Let me show you.
Were you in the path when we had this eureka moment?
Actually, that doesn't work like this. It was, you know what really triggered me? If I'm very honest, I read Itzik's article and I still was not tempted to do anything. I didn't like the solution anyway. But then he used words like, for decades it was impossible to optimize temporal queries, now there finally is a hope. What? No, like I'm bringing the light. They were, you know, to like we the king or we the god are now giving you, and this was what made me, you know. Well, might be this, you know, it's from Israel, so it might be this kind of Jewish cultural thing. You know, 2,000 years ago, another one had similar problems. So this is what triggered me. Said no, no, can't be this solution, you know, the God's solution. No, let's be a little bit more modest and find different solutions. This was the trigger. Anyway, no, we are the best friends with Ezekiel. I told him earlier, you know, we always spend holidays together, write books together. Actually, I have a room named in his house, you know, so, but we are also competing in this kind of things. So, and the big reason difference is he's from Israel, so simply means that he's working always. I'm from Balkans, which means I'm lazy, I work only if I'm triggered. This was a trigger. So there, you know, like last July, I was crazy. I didn't answer phone calls. I woke up at 4 a.m. starting to work and did most of these solutions. And this one is so extremely simple that I was really, you know, I really had to check. Really didn't believe that nobody thought of it earlier. So I'm actually adding length as persistent column, so I will easily find maximum length. And I'm adding additional index, and everything took 73 seconds, exactly like initial. So it was extremely efficient. So what I have here is I have also length, and I have all of the 10 million intervals here. So let's see now how it works. So what I need, this is my given interval, right? So what I need to find the max length, that's it. And this must be either max length in the table or the length of this interval if it is bigger than the max length in the table. So far I must go to the left or to the right if I want to use right index. Okay? And then when I have this max as a variable, then let me copy the original query. Let me copy the original query, the one before relational interval. This I want to have it side by side. For example, this one. I want to have it side by side to show you what is the difference. Once I have maximal length, which is simple, then compare these two queries. So you see lower or equal upper of the given interval, this is this. Upper greater or equal than lower boundary of the given interval, this is this part. And this part is efficiently, so if this part is used as a predicate, then all of these rows from the right are automatically excluded. If I'm using lower index and this part is used, then also rows from the left, remember from the slide, that start before the beginning of my interval minus maximal length are also excluded. And then I have also this one need to check to get rid of false positives. If right index is used, then left nodes are automatically excluded with this predicate. Those who are too far from on the right are excluded with this predicate. And this one is then used to check for exact matches. And this one is not used with the upper index. So, let's execute this, and please note that I'm working in the middle of the data, where I had 11,000. No, this is the end of the data. Okay, let's start in the middle of the data. So I'm checking for the longest interval, right? Starting here. Checking from the maximal interval. I went too far. Let me also be sure that I have statistics I go on. So I'm searching for max interval, and then this is the query. So let's see the results. So these are these rows from the middle of the table. And please note, 3 logical reads just to get the maximal value, and this is actually what I needed. The best possible result, and thank you, but unfortunately, it has a problem. What is the problem? Well, in this case, this was extremely efficient. The problem is with this maximal value. Now, if I have approximately equal distribution of length of intervals, this is perfect solution. You don't need anything else. But if I have just one very long interval, just one, then my solution will read most of the data anyway. You see? So, okay, then you could say, yes, it would be still useful as with 2 partial queries, first excluding the the longest intervals and work on the rest of the data, etc. Okay, so you could have a, let's say, first query that in a column table expression selects only those rows with intervals longer than something, and if there are only few, you scan this, and the rest is sick. But then it immediately becomes more complex. So this is the problem with this solution. You see? This is the problem, and here I'm showing this problem. So I'm just having longer interval. Imagine that this is a constant. Imagine that I have one such interval in a table. If this is given interval, it is not a problem, because I'm actually searching for more rows. This is my condition. But imagine that I would add a row with interval of length 10,000, I immediately get much worse result, while relational interval 3 would still give constant result. Now, many times, like if you are talking about contracts and so on, then distribution of length is approximately uniform. So this could be just the right solution. And I'm really surprised because it's so simple. So simple, I couldn't find that anybody else would present it earlier. So, efficiency depends on interval length distribution. If you have if all intervals are long, no problem. Then you are actually searching for more rows because of small rows in overlap. The only problem is if you have mostly short intervals and then a couple of very long. Just one very long would spoil all of the results. Now, I love Davide Mauri, his way of thinking. Why not using spatial data? We have spatial indexes. So, spatial indexes are working on geometry. So, they were working on area. And basically, a line is just part of this area, and you can treat an interval as a line. So if spatial indexes are useful to seek for areas that can overlap, they can be useful also for lines and represent interval with line of time. And we have spatial indexes out of the box. So let's see. Very nice idea. So let's see how it works. So instead of having you see this is similar thing like with interval data type. Now I have a single column, which is geometry data type. And now you just insert these intervals and convert them to line string. And if this line is long only one point, then you have to convert it in point. Geometry data type simply doesn't allow lines that consist of a single point, unit interval. But please look at this. First of all, this casting for every row was extremely slow. So inserting 10 million rows was more than 15 times slower. So this is already problematic. Okay, also adding indexes additionally, so altogether it was like 20 times slower than initial, which was 70 seconds with building all of the indexes. But also you see this modified web condition and also relational interval trees return also false positives. The problem with spatial indexes is that you have two-dimensional indexes, so simply, how does it translate to this problem? Simply you get more false positives. More false positives, which means you read more pages than it would be necessary. So let's go directly to the middle of the data. Directly here. You could already feel that the query was not that fast. In this case, I get 654 logical reads. So initially it's better than initially when I had 11,000. However, not really extremely useful. But you get more or less constant performance. Please note this. This is interesting. Don't be confused if you see something like this. You see I have 259 logical reads and 408 read-ahead reads. This is because of spatial index. Without spatial index, this would be a bug. I was surprised when I look at this for the first time. I don't know, what is this? How can this be? Anyway, you see, performance is more or less constant. However, more or less constant. However, it is not really the best performance you can get. The solution is reasonably simple, but you have a couple of problems. Okay, it's not very efficient. It's definitely not standard. Spatial data types, okay, also if you use interval data type, you cannot move this to Oracle, but anyway. And you don't support strong typing. So it's kind of abuse of spatial data type, but might be also a quick and dirty solution, but the least efficient so far. Now remember that in previous presentation I defined unpacked forum for the purpose of enforcing non-overlapping intervals only in a table. So I put key on the, I put unique index on the ID plus unpacked forum, so unit intervals. Okay? So this is original set of intervals, this is unpacked forum, and this is packed forum. Okay? This is just a brief introduction to packed forum. So how does packed forum help us? Packed doesn't help us. Okay? Unpacked help us. We already know how we create it. Okay? So we can even store it, right? And then let's go and check the queries. Let's go and check the queries. So let's go to the unpacked forum. I created this auxiliary table of numbers, okay? And then this is table which looks completely like the original one, lower upper, just I don't need these indexes. But then I created a view with schema binding, which actually joins intervals on these numbers, where number is between lower and upper boundary of interval. So for every row from the original table, I get one row for one time point of the interval. Okay? And then I index the view. So now I insert the data, and index view unfortunately also slows down the inserts. Okay? So unfortunately, it is still not so inefficient as with spatial data, but slows down the inserts. Okay? Now I have this unpacked, right, which has, this is the time point. ID, so ID, this one has this time point, and there somewhere has also 16 time point and so on. Okay? But please note this, I had initially 10 million rows, my average interval has 10 time points, so I have more than 100 million rows in the unpacked form. Is this a problem? Yes, it could be. It's not that big problem as you think, you know, because first of all, original table is very narrow. In production, it wouldn't be so narrow. This one is definitely very narrow. So it's not that bad. But take a look at this. How do I now find which intervals overlap? So this is middle of the data. So I'm just creating a table variable, okay? Just creating a table variable with this, just creating a table variable with intervals unpacked, where n between this lower and upper boundary. Okay? So, then I just select distinct ID from this table. Okay? I could also use join. Then I just create distinct ID. So I get, you see, these intervals unpacked. Let's see the execution. This time I need the execution plan. You see, this is the execution plan. Okay? So, what I searched was all of IDs, where n between lower and upper, and I got all of the IDs from the unpacked form. And because I have a single column, a single index was used. And all I need is distinct. So all I need is distinct. And what happens? I got 6 logical reads. Instead of browsing the original table, I'm browsing the unpacked. What is the idea? Well, you see, in unpacked form, I have these time points. So I have my, let me again try to show you, but I don't want to query all of this use derived table. I don't want to query all of the 100 and more million rows. See? But I will just order by now. ID and n. Okay? So that's why. Okay, I need alias. And now, you see, so this interval has points 17, 18, 19, and so on. And if this interval wants to overlap with my interval, then these points must be in my interval, at least one of them. You see? And I'm using a single index over this number, and that's it.
Will you get the same result if you change it to distinct after in group 5?
Yes, distinct is actually internally implemented as group by. And now I can use this also for beginning of data. And I can use this also for end of the data. And I always get the same performance. And queries are pretty simple. However, I have a problem with inserts. Inserts into index view are unfortunately slow. Now, instead of index view, I can actually create unpacked table. I can create unpacked table at the same primary key. This is time point and ID. And now, you see, even with row compression, insert went down to 4 minutes from 17. It's still slower than original insert. But I think this is mostly a problem of Microsoft. Why is inserting index view so slow? Shouldn't be slower than your insert. But also what I gain with this tabular form is I also gain possibility to have compression. You cannot use compression on indexed view. So, space used, you see, original table used 566 megabytes. Intervals unpacked used 3 times more. This is with row compression, I get better results.
Where is your index stored?
This is materialized in the database. My database is growing. So you see, I have this database I created in advance. So let me show the simple report. So index 2 is materialized. So my database is already 11 gigabytes, you see. So now with compression, and I don't even need to rebuild with page because I will not gain much. I say because not many data is repeating. Okay. I can go directly to query, and now I query unpacked table, and queries are even simpler than with index view. And of course, they are even more efficient because typically cannot be less efficient because I also have compression. And remember, even with row compression, inserts were reasonably fast. They were still like 3 times or 3.5 times slower than original inserts, but you see, I get constant performance that cannot be worse than performance with an indexed view, and I have actually reasonably good insert performance. But please note, queries are extremely simple and performance is fantastic. And I don't have any problems with distribution of data. I will simply get only those I don't get any false positives. I always get only those intervals that actually overlap. They must have at least one time point in my given interval, and then they overlap, so that's it. The only real problem with this is that I created more than 100 million rows from initial 10 million rows. Now imagine, my average, this means that my average interval was approximately 10 time points long. If my average interval was 365 time points long, this table would be even bigger. But, in my opinion, this is the winner in longer terms. You see, all intervals are already here. So the problem is constant, which simply means that if you cannot afford this solution now, wait for better hardware. Now, this is just a matter of hardware, and you will be able to use this solution. But, as I said, we are not there yet. But you see, I already wanted to have unpacked forum because of constraints, and now it also helps me with performance. If at least Microsoft would do this properly indexed views, then I wouldn't even need to create this table. Okay? Now what about CLR data type? Remember, we have byte order. Well, I can do the same thing as with modified where clause. The only thing is that now I have a single index, lower only, I don't have the upper index. So this will automatically cut off efficiently intervals from the right side, and I must go enough to the left side to use the same index to cut off also rows from the left side. And I get false positives, so I still need to check with overlaps operator. The solution will be slightly more complex because I must go not just the integer to the left, I must go interval to the left. Because I'm indexing the whole interval, not just begin or end. Okay? So, let's see this. So, this is this interval data type, you already know it from the previous presentation. So, let me configure so I can enable CLR, but otherwise things are already deployed, I just need to enable CLR because I disabled it. So you see inserts were practically the same performance as original inserts. I got an index, this is how it looks like. So this is binary presentation, these are lower and upper, right, begin, end, interval. I can even calculate fork node automatically, you see. This is just a calculation, why not? I can also calculate the length. So everything used so far can be used also on this data type. Just let me show you the naive solution. Remember, we have this overlaps operator, so this would be simple naive solution. This is my given interval. I have to cast it to interval data type. Okay, I have to cast it, right? And then let's use the naive solution. And unfortunately, this is not a searchable argument, so I get full scan. You see, double the amount of original rows. I get full, no covering index, but full scan. So let's find optimized solution. This is the max length. Okay, I already know it, so I will shorten it. So I simply have to find begin going. So find an interval whose sort values are low enough to filter everything before that interval from the left. Okay? And the one that filters everything from the right, so it will be possible to efficiently use this index on this binary form of my user-defined data type. This one from the right is very simple. I just take the unit interval with upper plus 1. So everything that is 1 point after my given interval cannot even overlap. For the left, I must go with the begin, left enough. And then, so I must go from given left point minus maximum length minus 1. So this is the earliest begin of the interval that can overlap with 1. And length of this interval is just 1. Anything before this interval, this will be definitely before all longer intervals that have the same starting point. So any interval with sort order lower than this interval simply cannot overlap. And what now? I got index C, and I got the most efficient solution so far. A little bit more complex, but of course it works also on the begin and on the end. No problem here. Still fantastic performance. Also on the end, yes, no problem. But, oh, this works better if I put everything here. But, what is the problem? Well, similarly, this is kind of similar solution to modified web clause, which means that one very long interval would harm the performance. because I wouldn't be able to filter out so many intervals. I would get much more false positives. So the same problem. But please note that you have seen in the table, I already calculated all of the fork node and everything automatically, so I can use any kind of solution with this data type. So let's now go to we are approaching the end. We have two ideas. One I actually tested. So you see, basically the idea of spatial data type is that you use single column, also of interval data type, that you use single column, single index. But we have also XML data type. Okay? So why not? We have standard solution. XML is more standard than spatial, or even my data type. And we have XML indexes, right? And the XML index is used. Now I will just, maybe I can even run the query while I'm talking. So I created XML representation with a simple, you see, this is what is XML, just single column, lower, upper, maximally efficient XML. So then I create a table which is only ID and this interval, and then I create primary XML index, right, on this column, and then also property, because I will search for property lower and upper, and then I insert data. So this was slow again, okay, but we already have seen this performance. This is, half of my database is this stupid XML index. Half of my database. I don't know what SQL Server is doing, but half of my database is XML index. And this one, please note, this was original, because this one is already filtered. So it's 4 times less. And I will not even run this, but this was amazing. Remember, initially I had 11,000 rows. Altogether it's 23,000 rows. So we were always teaching that SQL Server by itself doesn't do anything worse than a full table scan. With non-searchable argument, with overlaps operator of my user-defined data type, I got 23,000 reads. With this query, I got 77 million reads. And I still think that this is my personal record, So when I tried to, remember initially it was 11,000. So when I tried to optimize a query, I made it 7,000 times slower. This is my personal record. So unfortunately this doesn't work. So then I dig a little more in XML, right? So use 2012 selective XML index, okay, which is more efficient. Modified, selective index, then modified actually 2 indexes, and modified also the query to use exist method. And with all this, I still get 8 times less efficient queries than in the beginning. So what does it basically mean? It means that XML is practically useless. Okay, you can use it. I'm not saying it's completely useless. You can store small XML data types, but never, please never index them. As soon as you introduce XML indexes, SQL Server lost its mind. Completely query optimizer. I don't know why is it doing it? If you can treat XML also as a string. So with a simple like predicate, I would get full table scan and that's it. Okay, I cannot use lower and upper, but I could use like. It wouldn't be the same meaning.
It must be converting it into another internal table and then reading that internal table.
Yeah, but how? What kind of table does it create? Query optimizer is counting pages. So how did it get to idea to go to 77 million pages, when full scan is, okay, maybe XML is less efficient, still 30,000 pages. So, actually, I had another solution that was incredibly efficient in every single situation. Always got only 3 logical reads. The solution has just one small problem. It didn't return correct rows. Otherwise, it was perfect. And unfortunately, I wrote a blog about this, and the first one to read it was Itzik, and you can imagine, your great solution. So I'm not showing that solution. But I will just talk about last idea. You know, I think in longer terms, Unpacked Forum is the way to go. If you can't afford it now, you just wait for better time. But can you do something in between? So I started to think, and I don't have a code for this yet, so this is just the algorithm, I'm working on it now. So I was thinking, how do we actually calculate, let's say, length of an interval? You see, let's say, I want to get the difference between current date, which is 3rd of April, right? And let's say 17th of May 2020. So I'm not calculating this in days, right? To fully unpack this, I would need all days. But when we do this calculation, we start on higher level. So it's year 2014, so it is 6 years. And I said May, so it is 6 years, 1 month, and I think I said 17, and 14 days. So you see what I got here, 6 years, 1 month, 14 days. If I convert this to rows, I got 6 rows for years, 1 for month, and 14 for days, so altogether 21 rows. And originally, if I would go day by day level, this would mean something like more than 6 years, 360 days, so it would mean more than 2,000 rows. So can I do something similar in a database? And yes, of course, the answer is yes. Now, these are dates, but you can do the same thing as with the interval. So, this is begin, end. So, you store, this is 19th of March 2012, 20th until 31st of March. But then we know that the whole April is covered. So we store the whole April. So this is not a date anymore because April 00 doesn't exist. So this is kind of string. But then we store the full May and full December. But then we know that full year 2013 is inside. So we store full year 2013 and then full year 2014, 15, blah, 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 till 17. But then we must store on month level again until we get to the August when we have to store on day level. Now look at the calculation. We need, let's say, if we go to the second level, we need 59 rows at the beginning and maximally 59 rows, this on the lowest level. And then higher level is minutes. And higher level is rows, higher level is days, months, years. So if you calculate this, you need approximately 400 rows to cover 20 years long interval on second level. This is pretty compact. And we are still representing all of the time points in Unpacked Forum. Now, how does it help me with my queries? Now, this is compact Unpacked Forum. How does it help me? Remember when I said in previous module, overlapping is also when begin of my given interval is between begin and end of intervals in table, or begin of this intervals in table is between begin and end of my searched interval. Now, please note that I have an index on begin. So this is simply a searchable predicate. This is not. This is not a searchable predicate unless, remember I have untagged compact forum. Now I define search forum. So this is my interval. All I need is to convert this begin to this forum. All I need is 3 rows on day level. This is day. So you see, what I will check, whether this begin is between begin and end, I will join to this compact untagged forum. I will join. So when I'm joining it, I can find either exact day, or maybe the full month is covered, or maybe the full year is covered. So I simply join this search forum, which can be created on the fly, with the untagged forum, and I have this condition fulfilled in a very efficient way. And then I have to union the results of this query with simple select on the original table. Now this one has a single predicate begin, so it efficiently uses an index. So it simply means that such a query should be extremely efficient, and you can have compact untagged forum even for very, very large intervals on very detailed level and still have reasonable amount of rows. However, as I said, I don't have code for it yet. This is the latest idea I'm working on, but I think it should work. I think it should work. I'm pretty sure it will work because I tested it already algorithmically. So as I said, at some point I will have to sit down, and I'm thinking like even creating these methods inside interval data type, a method that would simply give me the this compact untagged forum, and another method that would give me the search forum. And then you could just use, for building this untagged forum, just the apply operator on this data type, so you get enough rows or exact rows you need. So it should be also, building should be also fast applies, very efficient. So conclusion, okay. I guess at some point Microsoft should do something about this support. When you start dealing with performance, in previous model we found many solutions that simplified queries, simplified triggers. But on the other hand, we implemented some problems, performance problems, and when you deal with it, some of these problems become very complex. Some queries immediately become very complex. I would say like this: what would I do in production? This is all nice and so, but in my opinion, data type like interval should be implemented by Microsoft. Seriously, I did it just as a suggestion for Microsoft. And now I'm sorry that I did it. You know that foreword for this Transact SQL programming book was written by Lubor Kolar, who was program manager for Query Optimizer and SQL Server. And he actually wrote in this foreword that Microsoft was considering putting temporal support in SQL Server for many years, but now they can postpone because here is the solution in the book. So, no, I didn't want this. No, this is the opposite what I wanted. So he actually wrote this forward sheet. Now everybody, will be mad on me. So you are the one who is getting it, Microsoft is not doing. So in production, I would simply start with this modified web clause. It's so incredibly simple. Just add two predicates to this web clause, and your queries become immediately very efficient. And the only problem is, yes, if you have very uneven distribution. then your queries are inefficient even at the points where they could be efficient. In longer terms, I think Microsoft should do, as I said, interval data type and then unpacked forum. This should be the winner in the longer terms. If you have this weird distribution, then maybe, and you cannot afford full unpacked forum, then either compact unpacked forum could be a solution or relational interval trees. Any questions?
Your index view, if you turn that into a table, would that make it more efficient?
Yes, I actually did it, and the performance on Hertz was like 4 or 5 times better, so maybe even acceptable already. And you can also compress the table, so even the queries were more efficient. Okay, so we are at the end. We have some takeaways. I guess you were on the previous session. So here you have monthly free subscription for plural-site courses and discount codes for training kits, Transact SQL and data warehousing. So please come and take it. If anybody didn't take, do it. And thank you very much for being with me till the end of the conference. Thank you. And